Suppose we have a following situation. Suppose we have a series, infinite series, n from 1 to infinity of n, and we know that it's convergent. We want to figure out what it is. So what we often do is we start adding the terms. A1 plus A2 plus and so on, and we stop at some point. And we remember that is K partial sum. And we say, well, how about SK is going to be our approximation to our infinite sum. Okay, so that is our approximation. Then we definitely have an error in approximation, and you see what is going on. If we look at the series n from 1 to infinity n, that is A1 plus A2 plus AK plus AK plus 1 plus so on. So that is initial sum A1 from AK is SK, and whatever is left out is our error. So often we're interested to see how big is the error, actually how big is the magnitude of an error. Okay, so how good is our approximation? So instead of working with the infinite sum, we take its partial sum to the k and we wonder how accurate is our approximation. So that's what the next theorem is addressing. So the integral test. Error estimate. So we have a situation where we have infinite series, we have corresponding integral, and we assume that we satisfy the hypothesis of the integral test, and we also assume that the series and correspondingly the integral are convergent. Then that's a statement which you want to make. Then error, magnitude of error is going to be less than integral from k to infinity f of x dx. That is the integral test error estimate, and it says that the error is going to be at most integral from k to infinity f of x dx if we're under hypothesis of integral test and we have both integral and the series convergent. And it's you kind of see why that is happening from the picture. So we have our function y equals f of x. So we have our series. So we have our function, we have our series. And then we're going to draw our triangle, something like that. And you see if k plus 1 is somewhere here, and our error will be these guys. That will be our error. These rectangles is going to be our error. And you see where the rectangles will be less or equal than that area under the curve. And the area under the curve can be calculated by integral from k to infinity f of x dx, because that's k plus 1 if k plus 1 is here when k is here. So these rectangles will be together, will give us a cave error. They will be smaller than the area under the curve. And we conclude that area under the curve can be calculated by integral. So we conclude that's the conclusion over error estimate using the integral test. So let's do an example or two using that theorem. Example. Look at where if we look at the series 1 over n cubed and from 1 to infinity, we know it is convergent by p-test. And say what we do is we approximate our infinite series by doing S10, which is 1 over 1 cube plus 1 over 2 cube plus and so on, plus 1 over 10 cube. So we say that is approximately equals to our infinite series, and we wonder how accurate our approximation. In other words, how big, what is our upper bound, how big is E10. Actually, absolute value of it, well, in our case, it's not important. So let's try to do the calculations. We're going to apply integral test error estimates. So what you're going to get is E10 is going to be less than integral from 10 to infinity dx divided by x cubed. That's what integral test for error estimates is saying. So let's calculate the integral. So we switch into negative exponent. So we're going to get x to a negative 2 divided by negative 2 from 10 to infinity. So we're going to get negative 1 over 2x squared from 10 to infinity. Substituting infinity, we're going to get 1 over 2 infinity squared minus 1 over 2 times 10 squared. So when we divide it by infinity, we're going to get 0. Minus gives us plus. So we're going to get E10 is going to be less than 1 over 2 times 10 squared. So it's going to be 2 squared is 100, 2 times 100 is 200. So we conclude that E to a 10 is going to be less than now 1 over 200. So error in approximating approximate 1 over n cubed and from 1 to infinity by S10 is less than 1 over 200. So that is for this problem. So it's going to be less than 1 over 200. Let's do a slightly different problem. This is 1 over n to 4 n to 1 to infinity is convergent by p-test. So the question is, how many terms you will need to add to find its sum. Accurate. To within 0.01. Okay. In other words, what is n so that error is going to be less than 0.01. Okay. So that's a problem. Let's try to address it. We know that error is going to be less by the integral test error estimate is going to be less than integral from n to infinity x divided by x to 4. And we want to make it less than 0.01. If we can make that less than 0.01, that automatically will guarantee that e to n also going to be less than 0.01. So we're going to concentrate on our second inequality. So let's work on it. So we have integral n to infinity x to negative 4 x. Antiderivative will be x to derivative x to negative 4 is x to negative 5 divided by negative 5 from n to infinity. So that is negative 1 over 5 x to 5 from n to infinity. Substituting infinity, we're going to get negative 1 over 5 infinity to 5 minus 1 over 5 and to 5. First expression is going to be equals to 0 because infinity to 5 on the bottom is infinity, and 1 divided by infinity multiplied by 5 is 0. So we're going to get 0 plus 1 over 5 and to 5. We're going to get 1 over 5 and to 5. So we're going to take that and we're going to substitute it to our inequalities in the middle part. So we have e n, and the arrow is going to be less than 1 over 5 and to 5, which is less than 0.01. We concentrate on the second inequality, and we're going to solve it for n. So 1 over 5 and to 5 is less than 0.01. Multiplying both sides by 5 and to 5, you're going to get 1 less than 0.01 times 5 and to 5. So we're going to get n to 5 is going to be bigger than 1 divided by 0.01 multiplied by 5. So we conclude that n is going to be bigger than 5 1 divided by 0.05. So we're going to get n bigger, and at that instant we're going to grab a calculator, calculate that fifth root. We get n is going to be bigger than 1.82 something. Because n has to be an integer number, we conclude that n equals to 2 works. So for our particular problem, S2 will be in 0.01 from the actual value of 1 over n to 4 and from 1 to